Hello. Today we're looking at, or we're starting off to look at differentiation. And we're going to start off by exploring a concept that we call first principles. And within first principles, we have to understand this idea of limitations. All right, let's start by really examining what differentiation means in a graphical sense. So, for example, if I talk about a function y equals x squared, and I do a graph of this function, just put my axes in. Obviously, I have a x and y intercept at 0, 0. And I have a nice parabolic shape expressing this. And we can have a point 1, 1. What we're looking for differentiation, or in differentiation, is we're looking at the gradient of the tangent. Now, this idea, a tangent, what we're talking about a tangent here is a straight line. So therefore, it will be represented by a linear equation that sits on the curve. So if I have a look at my tangent at 1, 1, my straight line would look something like that. And obviously this would be a straight line except by mx plus c. And what we're looking for differentiation is differentiation is, in a graphical sense, trying to find the gradient of the tangent. So here, what we're looking for is this value m. Now, this value m is not going to be the same across different aspects of this graph. For example, if I choose some point in this region, this tangent is going to be sitting along the line just like so. And obviously, you'll have the equation mx plus c. And this m here will be negative, whilst this m will be positive. So we have to make that distinction, but we really need to understand what a tangent is. Now, the way that we start to have a look at differentiation, and I'm going to stick with the same equation, y equals x squared, and here's my quick sketch, y, x, is we're going to choose 2 points. And through those 2 points, we're going to have a straight line going through. Now, even though my graph probably should show that line does not, if you like, follow the curve, it actually cuts the curve in 2 points. This line that I've represented here is what we call a secant. And it's a chord. It's eventually a chord. And what we can do is we can say with our function, let's say we call our function fx, we will say that that's x squared, and we can have here x, and we can have some value x plus h. And if I look then for my gradient, okay, and my gradient equals m, what I'm going to say is m equals my rise over my run. Now, when I start looking at my y values, I can find them by plugging in fx plus h and fx because they're both correspondent to one another. And obviously, if I focus on this section of the graph, so I'll just do a line here to focus on it. Here's this point, the curve, the chord or the secant coming through. And what we're trying to find with our gradient is our rise over our run. So our rise here is given by fx plus h minus fx. And this is given by x plus h minus x. Now, what happens is we can cancel that out. And this gives our gradient an equation, and the gradient for the secant being fx plus h minus fx all on h. Now this is a good approximation, or it can be a good approximation, of what the gradient at a specific point on the curve can be. But it's an approximation. It's not an exact value. It's not an exact value that we can say the gradient is exactly this at this point. So what we want to do is we want to use, we want to go forward to our tangent, and we want to use our limitations to be able to do that. So what I'm going to do is I'm going to draw the graph again. Here we have our graph coming in. Okay. And this is our secant. But let's say that I want to find the exact tangent at this point x. Well, I have all this information where I have x plus h, fx plus h. So I have all of this information put in here with my graph. But what I'm going to do with my value is I'm going to slowly have h, and I'm going to reduce h. So what I do is I'm going to say that I'm going to limit h approaches 0. That means I'm making h really, really small. So what I'm effectively doing is I'm bringing my tangent even closer, or my secant even closer, till h is really small, and then I get my tangent running along so when h is actually 0. And what we say here is, therefore, our gradient of our tangent, which we're going to call dy dx, that's the term that we use for the derivative, or for the expression of the gradient of the tangent. And we're going to say that that equals limit h approaches 0, fx plus h minus fx all on h. And this equation here is our first principles of differentiation. Now what I'm going to do is I'm going to explore, well, what happens if I get asked a question that says, okay, find the gradient of the tangent of y equals x squared when x equals 2. Now, this could be find the derivative, okay, of y equals x squared, or find the gradient of the tangent. Similar terms, and they're meaning similar things. A little bit different, but still we need to understand what that is going to give us in terms of a graph. So when I look at my graph here, I'm going to put 2 in here, okay, and I'm saying fx equals x squared, and my gradient, or my tangent, should look like that. And what I'm trying to find is my gradient. So what I'm going to do is, before I do anything else, I'll just get rid of that, is I'm going to evaluate what fx plus h equals. It always helps to just sort of list these items as it is. So if I have x plus h all squared, obviously there's some expansion that has to happen here. H squared. Therefore, dy dx equals limit h approaches 0. And what I have here is fx plus h minus fx all over h, and dy dx equals limit h approaches 0, and I'm going to substitute my values in for fx plus h and fx. So here I'm going to have x squared plus 2xh plus h squared minus x squared all over h. And what happens in with first principles is you get some cancellations. So x squared minus x squared comes down, 2xh plus h squared, that cancels out here. And what I end up having is I have this equals limit h approaches 0 equals 2x plus h. And when h equals or approaches 0, this just equals 2x. Therefore, m equals 2, and like I was saying, what we're looking for is the gradient of the tangent when x equals 2. So that's what we're substituting in for the x here. So we would say 2 here. And that equals 4. So what we would have is we would have m equals 4.